Scientists may have finally proved that empty space isn't really empty. If you like my videos, subscribe my channel, and press the bell icon to turn notifications on so you keep getting all the major advancements in science and technology. For a discussion, write down your views in comments. Imagine shining a beam of light through what appears to be completely empty space. There is no glass, no water, no crystal, nothing that should alter the path of the light. Yet, according to one of the strangest predictions of quantum physics, even a perfect vacuum may be capable of changing how light travels. Now, astronomers may have found the strongest evidence yet for this bizarre phenomenon by observing light emerging from one of the most extreme objects in the universe, a magnetar. These extraordinary neutron stars possess magnetic fields so powerful that they can create physical conditions impossible to reproduce on Earth. Researchers studying a magnetar called 1E 1547, 05408, or 1A1547, have detected unusual patterns in the polarization of its X-rays and radio emissions that could represent the first direct evidence of a phenomenon known as vacuum birefringence. If the interpretation is confirmed, it would mean that seemingly empty space itself can influence light, and it would provide a remarkable opportunity to test quantum electrodynamics under conditions found nowhere else. The story begins nearly 90 years ago with the development of quantum mechanics. One of its pioneers, Werner Heisenberg, helped establish a picture of nature in which the vacuum is far more complicated than it appears. In classical physics, empty space is simply empty. Remove all matter and radiation, and you might imagine that nothing remains. Quantum physics tells a very different story. The vacuum can be understood as possessing fluctuating quantum fields, with temporary disturbances often described using the language of virtual particles. These particles are not ordinary particles flying through space in the conventional sense, but their effects can influence measurable physical processes. Under ordinary conditions, those effects are extraordinarily subtle. But place the vacuum inside an unimaginably powerful magnetic field, and the situation changes dramatically. Quantum electrodynamics predicts that the vacuum itself can behave somewhat like a material medium, causing different polarization components of light to propagate differently. This predicted effect is called vacuum birefringence. The name may sound familiar because birefringence normally occurs in physical materials. Certain crystals, for example, can split or alter light depending on its polarization. Vacuum birefringence is astonishing because there is no conventional material involved. Instead, the effect would arise from the interaction between the electromagnetic field and quantum fluctuations of the vacuum. The challenge is that the magnetic fields required to make this effect observable are extraordinarily strong, far beyond anything humans can currently produce. According to the researchers, detecting vacuum birefringence requires magnetic fields more than 100 million times stronger than the strongest fields scientists have created on Earth. Fortunately, the universe has built natural laboratories capable of producing exactly these conditions. They are called magnetars. A magnetar is a special type of neutron star, the incredibly dense remnant left behind after a massive star reaches the end of its life. Neutron stars are already among the most extreme objects known, packing enormous amounts of mass into a sphere only a few tens of kilometers across. Magnetars take this extremity even further. Their magnetic fields are the strongest known in the universe, reaching levels more than 1 trillion times stronger than Earth's magnetic field. These fields can influence particles, radiation, and the behavior of light in ways that provide astronomers with a unique window into fundamental physics. For this study, researchers focused on 1E1547 using NASA's Imaging X-ray Polarimetry (UAP), Explorer, or XBP. They also used the NICER X-ray telescope aboard the International Space Station and radio observations from Murayang, the Cyro Parkes radio telescope in Australia. Radio measurements collected by the research team helped determine how the magnetar's polarization changed as the star rotated. That rotational behavior turned out to be extremely important. As the magnetar spins, Its radiation sweeps through space, and scientists can track the polarization of the emitted waves. Polarization describes the orientation in which electromagnetic waves oscillate. By carefully monitoring how this orientation changes, researchers can reconstruct information about the magnetic geometry surrounding the star. In the case of 1Eon 1547, the observations indicated that the magnetar's magnetic and rotational axes are almost aligned. Even more importantly, Earth appears to view the object from a direction close to its magnetic pole. This combination creates an unusually favorable viewing geometry for detecting the subtle signature expected from vacuum birefringence. It essentially gives astronomers a privileged perspective on the region where the magnetar's colossal magnetic field interacts with the quantum vacuum. The researchers then discovered two particularly important clues. First, the X-rays detected by XP displayed extremely high levels of polarization. Second, the direction of that polarization remained closely connected to the magnetar's magnetic field in a way that was consistent with the radio observations. According to the research team, these observations fit the behavior expected if the intense magnetic field is influencing the quantum vacuum around the star. In this picture, the magnetic field affects the quantum fluctuations of the vacuum, causing them to become aligned with the field. Light traveling through this region can then experience different conditions depending on its polarization. The result is effectively a vacuum that behaves as though it possesses optical properties, despite containing no ordinary material that could produce them. What makes the result particularly exciting is that scientists have been searching for this phenomenon for decades. Vacuum birefringence has been predicted since the early development of quantum electrodynamics, but producing a definitive experimental detection has proven extraordinarily difficult. Earth simply doesn't provide magnetic fields strong enough to make the effect easy to observe. Magnetars, however, naturally generate precisely the extreme conditions required. The researchers, therefore, turned an object billions of kilometers away into a kind of cosmic quantum laboratory. Instead of constructing an enormous machine on Earth, they observed the polarization of radiation traveling from a neutron star whose magnetic environment is vastly more powerful than anything humans can create. But there is an important scientific caution. The discovery has not yet been definitively confirmed. The observations provide what researchers describe as strong evidence, but additional data and more sophisticated computer simulations are still needed to establish whether vacuum birefringence is truly responsible for the observed polarization. Magnetars are extraordinarily complicated objects, and other physical processes occurring around them could potentially produce related signals. Scientists therefore need to distinguish the predicted quantum signature from the many other effects generated by an extreme neutron star. Future observations could provide more detailed polarization measurements, while improved simulations could help researchers model exactly how radiation should behave in the magnetar's environment. If future research confirms the interpretation, the implications could reach far beyond this single neutron star. It would provide a new way to test quantum electrodynamics, one of the most successful theories in physics, under conditions that cannot be recreated in terrestrial laboratories. It could also demonstrate that the quantum vacuum is not simply a passive backdrop in which physical events happen. Instead, empty space itself could have observable properties that influence the behavior of light. The idea is deeply counterintuitive. Remove matter, remove ordinary particles, and remove everything we normally associate with a physical medium, and yet the vacuum can still leave a measurable fingerprint on a beam of light. Nearly 90 years after Heisenberg and other pioneers began developing the quantum picture of nature, scientists may now be closing in on direct evidence of one of its strangest consequences. A magnetar's colossal magnetic field may have transformed an apparently empty region of space into a natural laboratory for quantum physics. If upcoming observations confirm the result, astronomers won't simply have learned something new about a distant neutron star. They may have demonstrated that empty space is not truly empty, and that the vacuum itself can change the way light travels. The universe may have been conducting this experiment for billions of years, we may finally be learning how to read the